Hello students, today our topic of discussion is structure of nucleus. In Rutherford scattering experiment, a gold foil of T thickness is taken and the alpha particle, that is helium nuclei having 2 neutron and 2 proton without any electron, is allowed to scatter on this gold foil. Maximum of the alpha particle just they crosses the gold foil and traces the forward path or the straight path, but few of them is scattered by with an angle of theta. To find out the number of particles which scattered with an range of angle theta to theta plus d theta, we can easily find out what is there. It means what is there in the gold foil, or we can discuss about the atom or the nucleus. This is the importance or significance of Rutherford scattering experiment. According to the calculations of the Rutherford scattering, uh, a formula is obtained where the number of scattered particle in the angle in between theta to theta plus d theta, it is found to be dependent upon directly proportional to the fourth power of the angle theta by 2 cosecant square raised to power 4 theta by 2, or you can say that the number which is obtained here with the help of detector, this number of this alpha scattered particle, it is depending upon this angle, and this is how it is depending upon, that is inversely proportional to sine raised to power 4 theta by 2. Second, the number of scattered particle also depends upon the thickness of the material on which the particle is allowed or the projectile is allowed to be scattered. This is the T thickness of the gold foil. If T is changed, the number of particles obtained here, the alpha particle which are scattered here within a range of angle theta to theta plus d theta, that is also going to be vary. It means this thickness is also playing an important role in these scattered number of particles. Third factor which can affect the number of scattered particle is the time of the measurement or time of the observation or time of the experiment. If one is performing this experiment for 5 minutes, he is getting some and let us consider annual number of scattered particle there. If another student is performing the same experiment for 10 minutes, the number is going to be large. As the time increases, the number of scattered particles, because the projectile are you are allowing the projectile to fall on this scattered material or scattered center for a large number of time, the number of alpha particle is going to increase, so the number of scattered particle is also going to be increased. Third one, the number of scattered particle is directly proportional to ZE. What is ZE? ZE is the charge on the nucleus of your scattered center. Let us consider this is an nucleus of your gold element, and this nucleus consists of a z number of protons, and we know that the charge on an proton is 1.6 into 10 raised to power minus 19 coulomb. Then what will be the total charge on this nuclei? The total charge on this nucleus is Ze. If the Ze is very large, the scattering or the number of the particles is going to be here very large, because we know that alpha particle has two protons, it means it has 2e charge, and this positive charge particle will be opposed by or scattered by this positive charge center or the scattering center. It means if we are just enlarging the magnitude of this nuclei or this scattered center, the number of the alpha particle are going to be increased in this solid angle. Similarly, uh, the number of scattered particle is also depending upon the kinetic energy of the alpha particle. Let us consider this alpha particle is moving very slow. If this alpha particle is moving very slow, then there are maximum number of chances it is going to be deflected in the direction of angle theta plus d theta. But if this is a fast moving alpha particle, or it is a alpha particle having large kinetic energy and magnitude, then this alpha particle has a tendency that is going to be in the forward direction with small scattering, or with no scattering, or with a small displacement, or with no displacement, because of the energy. It means if the energy of the alpha particle is increased, or the kinetic energy of the alpha particle is large, then the number of scattered particles in the range of the angle theta to theta plus d theta, which is going to be small. Hence, these all are five factors which can which can change the number of particles here. What is the significance of just studying the Rutherford scattering? Uh, with the help of this Rutherford scattering, or with the help of these scattered number of alpha particle, we can find out there is something inside the gold foil, and that something is mentioned as the nucleus. It means the first consideration, or the first conclusion, the first result with taken with the help of Rutherford scattering experiment is that there is something present inside the nucleus, and this is nothing. It present inside the atom, and this is nothing. It is termed as the nucleus. But the size of the nucleus is not very large, because the number of the particles scattered here is very small. It happens, it is possible only when this point, or this space is small. It means there is nucleus, but the size of the nucleus is very small. It means the size of the nucleus is very small. Next, what is the charge on this nucleus? We know that alpha particle, that is a positive charge particle, can be repelled with the help of, or can be scattered with the help of a positive charge particle. It means if it alpha particle is going far away, not coming towards the ZE, it means this scattered center is positively charged. And the third conclusion is the charge on this nucleus is positive charge. It means the protons are present inside the nucleus. Due to the size, and we can easily find out the mass of this nucleus, it is assumed that the nucleus consists of positive charge particle, but this scattered center is heavy one. Hence, it is find out that it consists of proton as well as neutron, because if neutron are present there, then only we can explain the mass, or the mass density of this nucleus, or this scattering center. Now, on the basis of the above results, or on the basis of the above conclusions, we can easily find out the distribution of positive particles inside the nucleus, that is protons, the per unit volume, and we can find out the charge density inside the nucleus. If we are studying the charge density inside the nucleus, it means we are just discussing the distribution of protons inside the nucleus. It means the charge density inside the nucleus is due to only the protons, because neutrons are the neutral particle there. And on calculating mathematically, we will and the results from the experiment of Rutherford scattering, it is find out that the charge density of the nucleus varies like this, where R is representing the distance from the center of the nucleus, and it is in Fermi meter, that is 10 raised to power minus 15 meter. And this charge density is nothing, it is Q upon V, that is charge per unit volume, because the nucleus is considered to be a spherical space, and if the radius of this spherical surface is increasing, the charge density is also going to be changed. Let us consider there are three nuclei. This is the heavy nuclei, and this is the lighter nuclei, and let us consider this is the nuclei in between the heavy and the lighter one. For heavy nucleus, As we are seeing this graph, the charge density remains constant for a large value, for a large distance from the center of the nucleus, and after a certain distance the charge density gradually goes on decreasing, but the charge density is not equal to zero anywhere. At r is equal to infinity, it is going to be zero. It means the nucleus has not sharp boundaries. Let us consider, if we draw this graph, or we show this graph on the diagram of the nucleus as a spherical, as a sphere. Let us consider this is our nucleus, and this is the center of our nucleus, and this is the distance which we are talking in, gradually increasing. In the first element, that is heavy element, this charge density remains constant for this distance. Let us consider this as r. It means there is a uniform distribution of protons for this space. After that, the number of proton, the number of positive charge particle gradually decreases. Here the positive charge particle are in large number, and after that the number of charge particle from this distance to this goes on decreasing. But there is no sharp boundary of this nucleus, because the charge density or the charge is present at infinity. It means can be present at infinity. It means there may be proton here, there may be proton here, there may be proton here. This is the overall representation of this graph. If we are taking some lighter particles, let us consider this is our oxygen element. This space is very small. It means the charge density remains constant for a small distance, or charge density remains maximum for a small range, and after that it starts gradually decreasing. It means in case of oxygen, or in case of lighter nuclei, this space is going to be small as compared to the heavy nuclei. It means this is the only reason, or it is the distance from the center of the nucleus where charge density is maximum. Afterwards the charge density is going to be decrease, or it means the number of proton starts to decrease after this range, or after this space of the nucleus. For mid elements having not a very small number of protons, or very large number of protons, this is the charge distribution. This lies in the range in between the lighter nuclei and the heavy nuclei, and after certain point the charge density starts going to decrease. It means the number of proton going to decrease after a certain range. Now we can show it with the help of this diagram. Also, the core or the center of this diagram indicates the number of protons is very large, and after that the number of proton gradually decreases, and we can't indicate any sharp boundaries of the nucleus, because according to this explanation proton can be present at infinity also, or we can say outside the nucleus also. If we are indicating that this is the limit, or this is the boundary, or this is the surface of your nucleus, according to this the proton can be present anywhere outside the nucleus, and so, nucleus is without any sharp boundaries. Next, according to Rutherford scattering, neutrons and protons both are present inside the nucleus, because the nucleus is heavy and it is small size. It is heavy. It means with proton there are neutron also. Now we will discuss about the mass density. If we are discussing the mass density, it means we are discussing the distribution of nucleons, that is neutrons and protons, combinedly with it from the center of the nucleus. Let us again consider this is the center of the nucleus, and it is we are moving towards the positive x-axis. The distance from the center of the nucleus is increasing. The distance or the range of the nucleus or the dimensions of the nucleus of Fermi meter. So we have taken this Fermi meter here of femtometer, that is 10 raised to power minus 15 meter. Here we are representing the density as rho r, that is the function of the distance from the center of the nucleus, and rho here it is mass per unit volume. And again we know that volume, it is the nucleus is a sphere, the volume is going to be V is equal to 4 by 3 pi r cube. Again we draw this graph for three nuclei or for three elements. Let us consider this is the heaviest element and this is the lighter element, and this is an element which is lying in between the heavy element and the light element. Now for all the three elements, heavy element, mid element or lighter element, we are just finding out the maximum mass density in all the three cases is approximately same, that is rho naught. This is the maximum mass density. It means number of neutrons or number of protons or number of nucleons are lying maximum in this range. The number of neutrons is very large for this range of your distance from the center of the nucleus. This is a point where the mass density becomes 90% of its maximum value, and this is a point here where the mass density becomes the 10% of its maximum value. Again, if we show that this is the point at the heavy nucleus graph where the mass density becomes 90%, and let us consider this is the point where the mass density becomes 10%, and the distance in between these 2 points, this is of 90% mass density and this is 10% on the same graph, on the mid graph. This is the distance in between these 2 points, and that is the density drops from 90% to the 10%, and this distance is represented here by a, and it is approximately same for all the nuclei. After a certain point in at every nucleus, at heavy nucleus, the mass density is going to be gradually decrease after a long distance, and in case of lighter nuclei, the mass density decreases earlier as compared to the heavy nuclei. Now, what is the radius of the nuclei? This is the distance from the center of the nucleus where the mass density becomes half of its maximum value. So in this way we define the range of the nucleus. The radius of the nucleus is a distance from the center of the nucleus where the mass density becomes the half of its maximum value. This is your radius of nuclei, and this is an average value, not an exact value, because already we are not indicating that this mass density is going to be zero anywhere at a distance r. It is going to just touch this graph only at x-axis only when r tends to infinity. Again, there are no sharp boundaries, but we are just defining the boundaries by the average value of the radius. It is a distance where the mass density becomes half of its maximum value. Now, if we just draw this graph with the help of an equation, then we will obtain this type of equation, or we can say that from this type of equation we can obtain this graph where rho is representing the mass density at any point with the distance r. Let us consider this is rho, this is rho, this is rho, this is rho. It means as we are increasing the distance from the center of the earth, we can find out the different mass densities and how they are related, or how can we calculate. This is the maximum mass density. This is the point which we are indicating in this equation. Then this is 1 plus e raised to power small r, that is representing the distance from the center of your nucleus. Capital R is representing the average radius or average distance, where this is the average distance where the mass density becomes half of its original value. And what is A is the distance where the charge mass density becomes gradually decreases from or drops from 90% to 10%. From 90 it is the reason or it is a distance in which the mass density uh, from 90% decreases to 10%. It is a distance, and it is approximately of 0.5 Fermi meter, or 0.5 into 10 raised to power minus 15 meter, almost for all the nuclei. Now we divide the nucleus into two parts. One is known as a central core, and another is the nuclear shells. In nuclear shells, the protons and neutrons are just moving inside the nucleus as the electrons are moving outside the nucleus or around the nucleus. This central core, it is the reason where we are getting the mass density at very high values. This is representing your nuclear core, and after that these where the mass density is going to be decreased, these can be represented with the help of the nuclear shells. And the thickness of the nuclear shell is approximately 4.4 E. Let us consider if it is your central core of the nucleus, and this is the region of your nuclear shells, then this region of nuclear shell, it is approximately of the order of 4.4 E, where E is equal to 0.5 into 10 raised to power minus 15 meter. Hence this is the core of the nucleus, and this region, that is of the thickness of 4.4A, it is representing the region of nuclear shells. With the help of all these conclusions, where the radius of the nucleus is depending upon the mass density of the nucleus, we find out that this is how we can represent the radius of your nucleus if you know the number of nucleons. A is representing your atomic mass number, which is a combination of neutrons plus protons. It is indicating the number of neutron and proton. Where R naught is representing a constant having value 1.2 Fermi meter. It can vary from 1.2 to 1.5 Fermi meter, that is 10 raised to power minus 15 meter. If you are increasing the number of neutrons and protons, indirectly it means you are increasing the size of your nucleus, or you can increasing the radius of the nucleus. Now with the help of this formula, we can find out the size or the radius of any nuclei if your atomic mass number is known. Let us consider if A is equal to 27, then the cube root of 27 is 3, then 3 into 1.2 is equal to 3.6 Fermi meter. It means for A is equal to 27, if atomic mass number is known, we can easily find out the size of your nucleus. Let us consider we find the size of a proton, and this is your H11 nuclei, where there is one proton and one electron, but there is no neutron. If A is equal to 1, then the cube root of the 1 is 1, and R naught into 1, it comes out to be 1.2 into 10 raised to power minus 15 meter, and this comes out to be the radius of a proton. But the proton can't exist independently, so we can't say that this is the radius of your nucleon.